Hello and welcome. Here we are in lecture 2. So we're going to get right into the coding right away. So if you remember from last time, we motivated why we're excited about Agile hardware design, gave a pitch about the structure for this course, and then right away today we're going to get into it. So just give me a moment to get the right screen. And not just get into it, you can get into it yourselves. So as you saw on the Slack channel I put out this morning, that all of our lecture slides are available as Jupyter notebooks since they're all posted on GitHub. So you can go ahead and clone those yourself and play with them while we're talking. Additionally, I recommend for today especially to find that link in the README for Binder. That's a cloud service that can host these notebooks for you, so you don't need to install anything. You can just click that. It takes about a minute for it to launch that instance for you. And then you can run it there in your browser without even install anything. So that'll be great. You can play with the code while I'm talking and do your own tweaks and see, what makes sense, what doesn't make sense. You also can run it locally. There's instructions in that repo for how to install the various tools needed to do this. Maybe you don't have time to do that quite right now, but yeah, for sure by Friday if you want to, sure, that would be great. So it's kind of fun to play with the stuff and get out there. So what are we actually going to be playing with this stuff for? Well, we're going to kind of take this, iterative agile approach, right? As I keep talking about closing the loop. Well, by the end of today's lecture, you're actually going to see a tiny Chisel module actually running and being tested in simulation. And so in order to do that, we're going to need to cover a little bit of Scala, a little bit of Chisel, a little bit of testing, and then kind of put it all together. And so we're going to do a little bit of everything, close that loop, see the entire big picture, and then in the coming days and weeks, we'll be, going into more detail in each of those parts, right? We'll go into more detail about Chisel, we'll go into more detail about Scala, we'll go into about the testing infrastructure, etc. That's our goal, right? Get something working early, scale back the features, scale back the functionality, but get something going, get it go through the entire process, see the entire big picture, then start filling it in, improving, revising, etc. So let's talk a little bit about Scala then. So as I mentioned last time, Scala is this really nice language that runs on top of the Java virtual machine, the JVM. So there's a lot of nice properties it gets from that. Not only does it get the JVM's portability, but it actually interoperates with Java code. So it's kind of like a Java++ in a way, but it has some really nice features. The things that most appealed to the people that created Chisel were the fact that it was really well designed for making what's called a domain-specific language, or in particular, an embedded domain-specific language. That is, you can kind of not just write a library, but kind of do that strongly, or do that well within your own constructs. And some of the other features that kind of distinguished Scala originally, and as I said, Java's kind of copied some features over time, is it not only is object-oriented, but it really has a strong static type system. So Java is object-oriented and statically typed, but in Scala now you have type inference, right? So you can leave types out of things, but it'll infer things and still get the safety of static types. It's really nice. There's also really good support for functional programming. And if you haven't done it before, don't worry, we're going to cover that in about a couple of weeks. It's another way to kind of express things very gracefully and compactly that makes things very robust. One interesting philosophy of Scala is that they try to catch as many errors at compile time as possible, which at first glance, that may not sound like a feature, right? If anyone who's learned how to program a language, when you first learn a language, you spend a lot of time encountering and resolving compiler errors, right? And we've all been through the process, right? You write some code, you try to run it, you get a compiler error, you copy paste the compiler error into an internet search terminal, and then you see, we know what comes up, right? And so the idea of more of those errors may not initially sound like a good thing. But it is, right? The reason why is a lot of these errors they can find at compile time would be harder to debug runtime errors, right? So, by finding these errors sooner in the process, it actually saves you time in the end. And so a lot of strong static type stuff inside Scala is to kind of catch these errors early on where it's like, you know what? You didn't mean to do this. This is not going to be safe. And it's going to help you try and catch those earlier. And so kind of putting it all together, as I said, why is this good for making Chisel? Not only can it interoperate with all the Java stuff, so you can use Java libraries inside your Chisel programs if you want to, talk to some database or something, whatever you need to do, no problem. But the object-oriented and functional features are really the key pieces to make it really great. Those are really nice analogies in hardware, right? Objects, of course, are nice for modules. And then the functional programming is a really great way to kind of get that write one semantics kind of just very robust, functional, single assignment kind of style you have in hardware. Additionally, Scala has some really nice stuff inside their standard libraries, so it'll be fun. Cool, I kind of go on. Yeah, feel free to raise your hand or ask questions in chat to stop me if you have any questions. But so when you're running Scala, how do you run it? Well, there's two main ways of running it. The most common way is your standard compilation execution, like any other compiled language. So you compile it down to Java bytecode. It runs on the same JVM as regular Java programs do. In order to do this, you need to have a main function, and actually, because everything's object-oriented, that function needs to be inside of an object, and there's some rules about classes. We'll cover those kind of details later. For now, we'll kind of treat things as boilerplate and kind of progressively explain more and more how that works. And so, to actually compile and run a Scala program, you have to call the Scala compiler. You need to do various things and launch it. People very rarely do that from command line or from Makefile. Most often, you use some sort of tool to do it for you to kind of automate that process and understand what needs to be done. And the two most common ones are, number one is something called SBT, or the Scala build tool. We'll be using that throughout this course. It's kind of like a combination make and package manager. So both can build your project, but also can track dependencies and bring them in as you need them for your code. I also strongly recommend when you're writing code for this class to use an IDE. My particular personal favorite IDE is IntelliJ. And so why do I recommend IDE? Well, it's really good at capturing errors even earlier, right? So I mentioned how Scala, can catch errors at compile time. An IDE will underline errors for you as you're writing them, right? And so it's really helpful when you learn a language. It'll tell you right away, oops, you should not do this 5 more times. You should fix this issue right away. IntelliJ is quite aggressive and helpful at the same time of trying to suggest ways to improve your code or how to avoid errors. And I think it's good for beginners to kind of be aware of a lot of these things. Another great benefit of IntelliJ is, of course, like any other IDE, you can right-click on code to go take implementation or see documentation. So it's really kind of easy to get a lot more information with your code. I think it's really, really helpful. And this is coming from somebody who's hardcore about text editors otherwise, but for writing Scala and Chisel, I use an IDE, recommend it heavily. Some students really, really, really like VS Code, and you can still use that like an IDE for this course. So there's instructions how to install something called Scala Metals, which is going to provide a lot of the IDE-like functionalities for code lookup and syntax highlighting, syntax underlining, I should say, for Scala. That's kind of a nice feature. Cool. But okay, so main way of running it normally is, compile and execute, and use some tool that kind of orchestrate all that for you. The other alternative, which is kind of nice, is you actually can do it as like an interpreted language. Even though Scala is a compiled language, it does have a REPL, or a read eval print loop kind of way to play with it. Like you may play with Python, a command line, kind of a similar way in its own interpreter. And so to launch the REPL, as simple as on a system that's installed, you can type Scala and boom, you have a REPL. This is kind of handy sometimes when you want to see how certain things play out. So if you want to just write 1 or 2 lines of Scala to kind of see I should try syntax this way or that way. It's a really helpful way to kind of do things. And the REPL, even if you aren't intentionally using it, we are all unintentionally using it when we actually are using the Jupyter notebooks. So the Jupyter notebooks for this course, we're kind of running a couple lines of Scala at a time. Those are all built on extensions to something called Almond. So Almond is this particular project which aims to make Scala kind of more interpreter-like. So you actually can have Scala code that just executes line by line, doesn't need to be inside of a main or an object or anything. And that's kind of how we're bootstrapping this whole process. And the way that's all working under the hood is actually treating this like a REPL. So long story over, you can run Scala both as a compiled program or with a REPL. So what are we actually going to use Scala for? Well, it has the same kind of types you're used to in most languages, int, float, long, double, byte, char, and string. So int and float, those types are actually 32-bit as part of the language by default. You can go ahead and, write some things out. So here I'm just kind of using in, the REPL mode. And yeah, so here I have some expressions, and we're going to let it run. It's going to take a second for the JVM to launch. I should also point out that I'm actually running this on Binder itself, and so perhaps maybe I lost my connection. Hopefully I didn't. If not, I have a local one I can fall back to. It's taking a touch too long. I'm a little bit worried it may have died. No, it says it's fine. Okay. Well, while it's thinking about that, I might go switch over to the local one, and that hopefully will execute right away. There we go. Great. And then did the other one come back as well? No, it's still running. I don't know why it happened to that one, but great. So local one works at least. And so a couple things to point out. So yes, you can, do simple math. You can have strings. They're denoted by the quotes. Notice how I didn't bother using semicolons. And actually, look at the Scala code. Semicolons are there. They do indicate the end of a line, but they're actually rarely used. And rather than being like Python, where it's strictly based on white space, the compiler just looks at syntactically what you're doing and recognizes, does this parse out as a valid expression or not? If it doesn't parse out as a valid expression, it's going to tell you it needs a semicolon, but I've just about never had to do that. Unless I do anything kind of silly with white space or something and mix up lines. I've just been able to kind of write Scala code without semicolons. That's kind of recommended by most style guides. It's pretty nice and clean that way. Let's keep going. So as I said, it can do type inference, right? So turns out, like in some languages like Java, there's, basic types and, more complicated objects. In Scala, everything is an object. And everything was referred to as statically typed, meaning its type needs to be known at compile time. So nothing is going to be found out late like Python. But what's nice is we don't have to always give the type specifier, right? You can do type inference and figure out what we mean. One other interesting quirk is that the type goes after the thing. So for example, if I start number 4, we're going to ask the interpreter to infer a type for that. Here I'm saying, let's make a 4, and I'm telling you it's an integer type. Or I could tell you it's a float type, or a double, or a car. And so if we go ahead and evaluate this, it's a reminder for those who haven't used Jupyter. If you do shift enter is how you evaluate these cells. Okay, you can see what happened, right? So 4 by itself, the inference engine on a literal side, that was an int. I told explicitly it was an int. Okay, that matches up. Of course, here, the float, double. This is the value for the car, which, when it's viewed, may not be printable. Who knows? Additionally, for a lot of things, you can, when it comes to type conversions or casting, the way in Scala to do that is typically with dot and then to something. So you can kind of do things like that. Cool. I'm going to pause for any questions so far while I see if the other thing is recovered. Nope. So what I'm going to do is actually just going to kill this binder and launch another one. I'm going to want the binder for later. That's why I kind of want to run it from there if I can. Okay. And then let's keep going. So here's one of the things where Scala starts differing from a lot of languages that we have seen before. Is actually every time you declare a variable, you need to tell it what kind of variable it is. So once again, it's kind of this strong type system coming out. So actually, variables can be declared as either mutable or immutable, meaning once you've created it, can you or can you not change its value? So in most languages we've had so far, most variables are mutable, right? And you can reassign them, and that's kind of like what you're used to. However, if we can avoid that, it's actually going to be a way to make much cleaner, much more readable code. And so we can have what's called an immutable variable, which, like you've seen in other languages, it's a const or a constant. And we're actually use that in the common case. So a val you can only assign once. And doesn't mean you can't have multiple function evaluations or whatever, multiple loop evaluations, but the val is only assigned once. And this kind of leads to very nice kind of clean code. And so, for example, here I've declared, 2 variables, one as a var, one as a val. So you see, for example, if I just evaluate this, okay, yes, it recognizes I made this variable mutex and I signed it to 2 and I have, and so at this point, they're both kind of listed as, the values and their types. For example, if I was to try to make this a val, it's going to complain, you can't do that. You're reassigning to it, right? And so at first glance, you might be thinking, oh wait, why not just make everything var all the time? That seems to be more capable. Trust me, you're going to be happier making things val, not just most of the time, but basically all of the time. And the reason why is it'll help you catch a lot of errors. And there's a few times you do need to reassign a variable, and the way that kind of forces you to rethink how you structure your code in terms of perhaps choosing to use another function call or another loop invocation or something. Using val all the time will make your code better. That being said, there's 1% of the times you should use var. And I will periodically show it in lecture as a way to kind of contrast different coding styles. And so sometimes my first laboratory students get into using var, but then they never stop the rest of the quarter. I recommend using it sparingly from the beginning as you can, and then even if you're using it sparingly, try and use it less and less. I spent years in this large Scala Chisel project where I basically used var 0 times in 2.5 years. So you can definitely go without it. I think when you learn the times, there are times where var is going to be cleaner both for code and for performance, but really, really want to encourage you to use val when you can. And let's check on that other binder instance. How are we doing? Oops. I think it's up and running. Let's go ahead and launch it. This is the binder instance. Let's make sure that it's actually evaluating. Binder might be getting slammed by everyone from this class. That may be part of the issue. I don't know. It's a free notebook hosting service. Yeah, it might be... Oh, there it came out. Great. All right, well, let's go ahead and try to use this from now on. So this is a button to launch the presentation mode. Okay, and so let's go ahead and, we can run this. Great. Okay, we're rolling back on binder mode. Great. So the reason why I was covering that little bit of Scala is that Chisel really is just a Scala library. At times, it kind of feels like its own language, but really when you're writing Chisel code, you're writing Scala code. It just so happens to be even a particular library, right? And so what's nice about that is we get all the power of Scala, right? So if you've written other hard design languages, they often get the harder part quite well. But when you want to do other things like, to automate various things, to script various things, write out the files, read stuff in, talk to a database or whatever, that's just not there, right? And no, now in this case, we have the full power of a nice programming language Scala, as well as the entire world of code available for Java, right? And so it's pretty cool. And even though, like I said, technically you're writing Chisel, you're writing Scala, sometimes it does really feel like a different language, and that's because they're using these features in Scala to make it nice for writing an embedded DSL. And so there's some features in there to kind of clean the syntax a little bit. And so you don't recognize, it may not always seem like you're writing Scala. It actually looks like you're writing something else. And so just to give you a sense of how this all fits together, you're going to write your Chisel design as a Scala file. So .scala is going to be what it is. You're going to pass it to the Scala compiler, and it's going to run. When that program runs, remember we're making generators in this course, not just a single hard design, but a hard design generator. It's going to talk to the Chisel library, and the two of them together are going to create the output, which is what we call a circuit, or in particular, is what we call a fertile file or a .fertile. And so fertile is the language used to represent the hardware coming out of our tools. From there, that can be turned into Verilog or whatever else you want. And so fertile is actually technically an intermediate representation. We'll come to that at the end of the quarter, but technically it means it's kind of this format we can use to turn into other things, right? So we actually can pass this off to simulators to do simulation. We can pass it to backends to turn the Verilog or other languages. But from your point of view, what I want you to keep in mind is, yes, you're writing Chisel as a Scala program. It's going to execute, and a lot of the Chisel functionality comes from a library when we get out our hardware design, which we then can do other things with. So because of that, we can just load it in, right? So I'm going to go ahead and launch these two cells. The first one to take the longest. It's going to go ahead and actually go download a lot of packages to build all this. And because I'm running in the cloud instance, this cloud instance has never done this before, so it takes a while. If you set this up locally, This will happen much quicker after the first time because, of course, we'll cache and remember those packages. So yeah, we're going to let it go ahead and bring in all those packages. These are all the various things it needs to run Chisel and all of its dependencies, and this has all been kind of handled by the tools automatically. Then we're actually going to import the Chisel libraries into our, namespace. Okay, so we did all that. Then what? So let's go ahead and make some Chisel types. So in Chisel, really the most common type you're going to use is either bool or uint. So what are they? Well, bool, as the name implies, a boolean. And although the name is similar, it's not to be confused with the boolean in Scala. So even though Scala has a boolean, Chisel has a bool, they both represent true or false things. They are distinct types, and kind of keeping in the spirit of Scala's type system, they're intentionally distinct, right? That way, we can't accidentally pass in a Scala type or we need a Chisel type or vice versa, right? They are distinct types. So for example, if I evaluate this little text cell over here, we can see that, here I declared something as a bool, and the way to declare a bool in Chisel is with .b. So .b is actually invoking, Chisel library and saying, hey, make this the bool type. If I don't mark it that way, I get a boolean, which is the one from Scala, right? But so if we really want to have a literal for a boolean in Chisel, you can use the .b, and you can kind of see the various ways of writing this out. Here I've declared my bool. For example, if I tried to make this a Scala boolean, this should yell at me, right? Because those types don't match. But okay, that's fine. So obviously, of course, in hardware designs, you often have boolean things. That's very common. Next most common is a uint, right? This is kind of like a bus in Verilog where I can now have a multi-bit thing, right? So as the name implies, uint is a unsigned integer. What's interesting about it is how big it is in terms of how many bits it is in hardware. That is something that you cannot specify, right? So a lot of languages are kind of forced to always specify all these bit widths everywhere. Okay, I want a 4-bit bus. I want an 8-bit bus. In Chisel, you actually can leave it unspecified, and the Chisel tools will infer a bit width. And it will do that based on what it's connected to and how it goes through various operators. Now, if that behavior is not quite what you want, you of course can always manually specify a bit width. But you'd be surprised how often you can only specify some bit widths and it'll infer the other ones correctly, and things works out pretty well. And that's kind of nice because it's a way to kind of make the code more robust and have less repetition, less things you can kind of break or get wrong. Make the tools do the work. It's another one of these course themes. And so, for example, if I just declare a number 6 on the interpreter, well, it's going to be a regular Scala int. If I want to make it a Chisel uint, I need to put the .u on it. Okay. And you see that, okay, for example, I'd ask for number 6. I didn't give it a width. And it decided that, what? The smallest uint that can represent number 6 is going to need to have 3 bits, right? That's what this is here saying. It's 3 bits wide. And it has the value 6. Alternatively, maybe I say, I want the value 6 as a uint, but I want it to be 8 bits wide. You can do that. You can say, here, I want this width. And so widths are .w. And of course, these are just kind of literals by themselves. You can assign them to variables, same kind of thing. Okay, you can have a uint for 4, which 4, the fewest number of bits to hold that is 3 bits once again. Or I can say I wanted 8 bits. And yeah, it will kind of adjust these naturally, right? So make this, instead of 6, I'm going to make it 16. It's going to make the field bigger in order to accommodate that. Right now it's a 5-bit thing in order to hold all that number. And then there will be a handful of times you're going to want an essent or a sign integer. And it works just like a uint. You need to explicitly request it as a .s. For example, I could make 2 as an essent, no problem. However, I cannot make -2 a uint, right? Because -2 is negative and uint is unsigned, so that's going to, tell me, oops, you shouldn't have done that. The literal is negative, right? But you get the picture, right? So, okay, we have literals. We've been doing some stuff with types so far, kind of playing around with it. I'm going to pause for just a second in case there's any questions. Okay, well, let's keep going. So in terms of what can you do with these variables, types, and literals, well, you can do operations on them, right? And so most of the operators that you've seen in other languages are here. So, you can do things like, logical operations. You can do bitwise operations. You can do arithmetic operations. There's only a couple things you need to watch out for and be careful for. The biggest one by far is equality testing. So for Chisel, when you want to compare something as equal or not equal, there's a distinct operator for this. It's 3 equal signs, yes, 3, as well as there is a not equal, which is equal, slash not equal, like this. So why does Chisel do this? This is one of those few times where the fact that it's an embedded DSL kind of peeks its head above the water, in the sense that the normal equals and not equals are kind of an important thing in Scala to be available for all objects, in order to kind of compare, are these objects equal, in kind of the object sense and the memory sense. And rather than overriding that behavior, which is possible, they chose to make a distinct operator, right? So this is one of those common mistakes that I think people make when they learn Chisels. Yeah, remember, for equality tests, it's got to be triple equal, and that's that case. Some other things to be aware of is that, depending on the operation you're doing, the result width, if you're not specifying your widths, will be determined by the compiler, and it follows certain rules. And if you forget what those rules are, there's this link here for what I call the Chisel cheat sheets, this wonderful document created by Richard Lin, where in there you can see for given operation and how big the input operators are, operands, I'm sorry, excuse me, it'll tell you how wide the output should be. And so, as a result, you can kind of go through that, right? So, for example, like if you're adding 2 numbers, in order to not lose anything, it's going to grow the result by a bit to kind of guarantee that. Those kind of questions come up. And then, okay, I'm going to pause for a second. I think I saw some chats coming through. Yes, going back to the last slide. Does Essent use 2's complement? Yes. It does. Yeah, so the sign type by default is 2's complement. Understand that level of detail is kind of, in many ways, hidden, in the sense that it behaves as a signed number would when you do various operations and the results you get. And the fact is 2's complement kind of creeps up more when you actually look at the Verilog that's generated and how the Verilog tools handle it. But yes, it's 2's complement. Okay, so then continuing on these other operators, you can see there are other ones. These are kind of the basic ones. There's things that are much more specific to hardware, things like extracting out certain bits or subsets of bits, filling in bits, concatenating things together, muxing, choosing between things, and something called reductions, that's reducing many bits down to a few bits or 1 bit. We'll cover those in coming lectures. I'm just kind of putting them all out there, giving you a high-level tour, and then we'll come back to a lot of these. So, for example, you could, have 2 uints and just add them together. Unfortunately, if I don't do this, it's not gonna. If I just run, it's not gonna work, because although this is valid, Scala as a Chisel operations look problematic. Part of the magic under the hood of Chisel is how it's doing things requires you to subclass certain modules. If you aren't in the right scope, it can't find the things it needs, so it's not going to work. And so, yeah, unfortunately, we're going to not be able to write one-liners of Chisel like that, but you can do that for pure Scala things. Okay, so then, if there's no questions so far, let's go ahead and make our first Chisel module. Okay, so here, what are we doing? We're going to declare a module that all it's going to do is internally it's an XOR gate. Okay, and so what do we have in here? Well, we need to declare our IO, or inputs and outputs, and what it does. And we'll kind of come back to all of these syntactic details on the coming lectures, but to kind of give you a tour today, you can see that yes, this is normal Scala. This is also normal Scala. Module is a key word from Chisel, so we're actually extending a particular parent superclass in the Chisel library. And we're declaring our IO, right? And so IO is also something special. And we're going to say, hey, I have these inputs, A and B. They are a bool, right? So remember that's the Chisel way of doing a binary signal. And then I have an output. It's also a bool. Okay. So we are kind of telling it the type signatures of the input and output. And then what are we doing? Well, to do the XOR operation, we're taking our two signals and XORing them together. So this is that caret symbol like a lot of languages for XOR. And in terms of accessing these signals, right, these are fields within an IO. So you kind of think of an IO as technically what's called a bundle. And the bundle is very much like a struct, right? So this is something that kind of holds together all these fields to us so we can access those subfields by simply dotting into them. And, here we've decided to do that. Okay, so we have, A XOR B. And then we're connecting this to the output C. So another thing to recognize is that when we're doing things in Chisel, we're actually not just assigning things, but actually connecting wires. We use this what's called a connection operation, so actually it's a colon equal. So you'll see both equals and colon equals frequently inside Chisel code, right? So equals are assigning a Scala variable. Colon equal is making a hardware connection, right? So it's kind of a key distinction. This is, I think, the key thing to understand is that I kind of appreciate that you're writing a Scala program that happens to have this byproduct side effect of making hardware. We'll cover that more on Friday as well. But I'm just going to kind of toss the idea out there now for today. And so if you want to kind of pictorially appreciate what we've done, we've declared, a module. So the diagram I drew myself of, okay, well, we have this module. There's an interface. So I have, this IO. And, yes, I have two inputs coming in, one output going out. And you can see, of course, internally it's connected to the XOR gate. Cool. Okay. Questions so far? Okay, well then, let's go ahead and evaluate this. So I've written up that module. What's the result? Well, it says, hey, I defined my class, my XOR. Great. So what can I do with it? Well, for today, we're going to do a couple things. We can look at what we actually did. So these are some nice shorthands provided in this notebook environment we've created. So we can instantiate an instance of this module and then ask for how it would look if it was produced as Verilog, right? Which so it's not only going to produce that fertile file I was telling you about, it's actually going to go ahead and run the backend as well to generate the Verilog, right? So it's going to go ahead and, as I said, elaborate the design, which is, creating the fertile file and then go through the process. And so, yes, so if we were to look at this as Verilog, print lines is a Scala feature to, print what's inside its arguments. We see, yes, okay, so this is the same module we just described as if it was written, in Verilog. A few small things I'll point out right now, but we'll come back to these in detail. You notice how I declared only, A, B, and C as my IOs, but there's clock and reset. Chisel has an implicit clock and reset in every module. It's actually really nice because most of the time you don't need to worry about declaring these signals. It's handled for you automatically, and they're passed around automatically. If there's ever a reason why you want to override that behavior or want to use your own clock, like in a multiple clock domain design, you can do that. There's ways to do that. But for the most part, it's kind of nice. They're just there. It's, to think about it, it kind of handles it. You have simpler code. Of course, the combination logic, we don't really need a clock. That's kind of a weird artifact for now. But yeah, so that's kind of nice. Another thing to point out is that normally to try and make your code readable, it ties back the Verilog to what produced it. So if you're writing like a big project and you're looking through it, it comments the lines with what Scala code created that line of Verilog. Because we're running this notebook environment, it's trying to do that same behavior, but it's doing that from these almond scripts rather than a proper Scala program. And so we get kind of these details like this, which aren't quite as helpful today, right? It was running on this, command.13.sc, but, that's not as helpful. But normally it'd be like, at, my class.scala line 17 actually is line of Scala, so you can trace it back to figure out what made what. But cool. So I wrote a little module and I got the Verilog for it. What else can we do? Well, this is part of why I want to run in a binder today, is we actually can try to visualize the circuit. So let's actually execute that. Fingers crossed this will work. This is going to require GraphViz to be installed in the system. And yes, there it works. So I don't have GraphViz installed on my laptop, but it does run just fine on this binder instance. And so yeah, so it actually went ahead and took that Fertile file, used another Chisel project called a diagrammer, which takes in hard designs in that Fertile format and then spits out files appropriate for GraphViz, a visualization tool. And so you can see, yes, here's my module where I have these two inputs that go into an XOR block, and it comes out as the output. And so sometimes when you're trying to understand how various modules fit together, this tool is kind of very helpful. But it's another way to kind of see it. And yeah, we're kind of playing with it, right? So in this case, I wouldn't worry too much about the syntax here. We're doing a little bit of a magic of kind of creating a late evaluating function here. But the key thing is, yeah, we can take our design, we can look at it as Verilog, we can look at it as a diagram like that, sure. Okay, and then maybe I'll pause here for questions actually, so I'll go back for just a second. Any questions so far? Cool, okay, well, we have our little design running. So let's kind of look at the back end. So earlier I showed you kind of the front end for Chisel, how it kind of all fits together. Oh yeah, sorry, someone's saying anything I can't hear. I'm sorry, was there an audible question? Let me double check my audio. Yes, I'm sorry, can someone say anything? I didn't know if there's any verbal things. Okay, thanks for bringing some attention. I can't hear you, so I'm gonna go ahead and try a quick hack over here and see if this will fix the audio. Yeah, try speaking again. Yes, I can hear you. Thank you. Was there a question I missed? I'm sorry. Oh, yeah, the question is, do I have things like XOR available? Yes, things like XOR are totally available. This is a, if I go back another frame, yeah, this operation is very much available. This is just an example of like, what is the simplest thing I could put into a module to show you the process. But yes, you go back a few slides, you can kind of see all the operators we have available. Yeah, these are all kind of available out of the gate, so to speak, no pun intended. And then we can kind of create our own additional operators, kind of using the nice features of the language. We can create our own abstractions and build up. But yes, things like XOR and all that, you can just call when you need to, and you can have big, complicated expressions or multi-line modules, no problem. Does that answer your question? I'm not sure I fully understood it. Oh, the question is for the visualization tool, how does it know how to visualize it? So the visualization tool actually just kind of, takes the easy way out and just writes XOR. And so it knows this is a binary operation because of the way it was kind of declared in the syntax. And it just knows it happens to be XOR. So someone wrote a special case for that caret symbol and recognizes that as XOR, but it's not an XOR symbol, it just says XOR over here. If you were to write larger designs and pass it to this visualization tool, if there are modules you've declared in your namespace, it'll represent those as boxes and kind of, encaps, oh yes, this is my foo, my module, it'll do that correctly. And for the primitive types, it'll do something like this, where for the primitive operations, it'll just kind of take the easy way out and say, inputs, output, and then label the operation. So visually, it's not as helpful as you might like, because you can't, just instantly glance at and recognize, oh, this is a mux or whatever, kind of have to read the label and figure out what it is. But yeah, it should be able to handle any fertile you throw at it. And it usually has kind of this cop out of just labeling the operation. No problem. Yeah. Why don't we go ahead and just make this arbitrarily more complicated just because we want to, right? So if we want to, let's say A XOR B or io.a. So now we've defined a new class. This diagram to right I drew manually, so it's not going to be updated. But then if we go ahead and, reevaluate the Verilog, we should see a slightly more complicated expression, right? You see the OR came in here. And then if I ask it to visualize this, we got to rerun this. It'll now show the OR. And this is something that happens with the version of Chisel you'll see in this notebook today. Hopefully later tonight, I'll be flipping a switch on using a newer version of Chisel, and this might go away or might not, depending on the situation. There's an intermediate temporary here. So oftentimes, the Scala compiler, Chisel compiler is very, very cautious, very, very careful, and it will create intermediate steps. So even though in the original code, I didn't, declare as multiple variables, I just kind of attached this directly. The Chisel generated version is very careful, and it kind of does things one operation per line. That tends to work out really well with the downstream commercial CAD tools. And so one of the nice features of Chisel is kind of like a way of linting your code, where you may have people writing very complicated Verilog, and that Verilog sometimes isn't quite perfectly parsed by the CAD tools, and that one corner case is what causes your project to fail. So having Chisel kind of take these things very carefully and doing one operation per line tends to get more consistent, predictable results from the CAD tools. But when it comes to human reading the generated Verilog, sometimes it can be a little tedious because there's these new variables created in order to kind of break up these complicated expressions in multiple lines. And so I'm pretty sure that's what happened right here. Usually you can recognize those things when it has the underscore as a leading name or a T in the name. So you can see, yes, we have this topology we kind of created where we had the XOR gate coming in, and then we ORed the result with that, and we can see how it kind of connects. And so, here we can see it's kind of this left to right precedence order of how to kind of evaluate all these things together. Cool, great questions. Yeah, I'm sorry I couldn't hear. I had the wrong audio set for my headphones. I will do an audio test for Friday then, before I start lecturing. So yeah, let's see, you can kind of play around with these and kind of run it. And like I said, in order to do visualization, that's not kind of like a default thing. That's using this package called Diagrammer, which is a Chisel project someone made. And in order to actually see the images, use what's something called GraphViz, which is, a common open source program, but that needs to be installed. And right now I'm running on a Mac. When you install GraphViz, you need to install like 25 dependent packages. So it's a little bit of extra work. And so usually when I need to use this tool, I tend to run my code elsewhere, which has easier access to GraphViz. In this case, this binder instance, just install that GraphViz for me so I can kind of run that. And from my point of view, just running in a browser, I can't really tell I'm running on binder versus locally. Other than the fact that GraphViz is available. Okay, so let's go ahead and keep going. So remember earlier I had this flow diagram showing how you went from a Chisel Scala program to getting the Fertile file. And the question is, what do you do with that Fertile file, that actual hardware circuit? Well, you can simulate it. So pass it into a simulator and, see the result of simulation. Or you can turn it into hardware. So the Fertile library can turn into Verilog, and you kind of just saw the output of that Fertile library turning into Verilog. And then, of course, with that Verilog, you can pass it off to conventional CAD tools, and they can go ahead and synthesize a design for ASIC or FPGA, whatever you're doing it for. Or perhaps even simulating, right? So, for example, in a lot of large industrial projects, they like to use Verilator to simulate their designs. And so they will, generate the Fertile file, it gets passed through the tool flow, and it creates Verilog, and that Verilog is passed off to this tool called Verilator, or maybe you want to use a commercial tool like VCS, and you simulate the Verilog there. And a lot of companies use that flow because they're simulating and testing and evaluating the same Verilog they're passing off to their CAD tools downstream. So it's kind of a nice congruence there to kind of have additional confidence in your verification. But for this course, we can kind of short circuit a lot of that steps by just doing things directly in Fertile land and never even getting to Verilog, right? So there's a simulator written in Scala called Treadle, which can run really quickly. That's what we're using right now. And that'll simulate it, right? And so Treadle can produce not only the output as a text, and you can have to do print statements inside your test cases. You can also generate a waveform, right? That's what .bcd is for. And so you can visualize your hardware design as a waveform and see how it's going over time. And of course, when you're doing testing or a simulation, you need somebody to kind of interact with your design, right? Because when you think about it, your program is describing or generating a piece of hardware, but that piece of hardware just exists, right? It's just, a thing. In order to actually have a program and run, you actually need to have a simulation, you actually need to give it stimulus. Okay, I want to make the input at this cycle have this value. I want to make the input at this cycle have this different value. And, you need to kind of give it stimulus, right? So you need to have some sort of way of making it happen. And so if you're using Treadle or anything like it, you can use what we call Chisel Test, which is a nice library to write programs in Scala that, can act as unit tests on your hardware designs. And those will be automatically kind of interacting with your hardware design over time in a simulation. I'll also mention a brief aside. So part of my investment in this ecosystem is one of my research projects is called Essent, and we're making a Fertile simulator, right? So we take in Fertile like Treadle or these other backends, and we generate simulators for it. So this is a project working on with some of my students in my group. And so with Essent, we're able to actually make really, really fast simulators. And so we are able to perform commercial simulators by doing some clever tricks in how we process design and generate a code for it. But yeah, so it's kind of cool. There's a lot of different choices once you get to Fertile. A number of choices here is growing. And for this course, the most common path will be using the Treadle, a nice Scala simulator. It's very simple, ready to go. It's not crazy fast, but for the size designs we're doing, it'll be more than sufficient. It'll be rare, even on a project with a large enough instance to have it take anything other than almost instant. And that'll be great. Cool. Alrighty, any questions about the tool flow? Okay, so let's go ahead and maybe try to use Chisel Test. Like I said, so Chisel Test is a way to write your test benches in Scala. So you're going to write a stimulus saying, hey, what do I want to do to hardware design? How do I want to kind of interact with it? And in particular, you can set inputs. You can also look at the outputs, and you can compare the outputs to certain things, kind of like an assert, right? So this isn't the only time I'm going to cover this in lecture, but just for today, as I said, we're kind of covering everything in a very cursory, surface level detail to kind of see the big picture, and then we'll elaborate. So what are the main operations inside a Chisel Test program? Well, there's poking, which is setting the value of a wire. There is peaking, which is to see the value of a wire. So wires are known as things inside your design. And then if I just want to read the value of a wire, if you actually want to check for a certain value, that is to make sure it does the right thing, you can read and compare. It's kind of like an assert statement, right? And that's the expect. Okay, so let's go ahead and see these in practice, right? So if I take my hardware design, which we previously declared, and we go ahead and run it. Here we've declared a test. There's some syntactic sugar. I can just write test and then, I'm declaring an instance of it. And then given that instance, what do I do with it? We'll cover this more in detail in the coming lectures, but for now, you can treat it as boilerplate. Well, I'm going to poke values on the two inputs and then compare it, right? See what the result is. And so, if I XOR 0 and 0, we expect to get 0, right? If I XOR 0 and 1, we expect to get 1, etc. Now, if I run this, it's going to fail because we messed around with the internals of my XOR, right? So yeah, it says, hey, wait a second. It did not equal the one you expected, right? And we expected a 0 and we got a 1. And so right, the line number is a little bit hard to read in this situation, but just remembering our change we made, right? Because we ORed in A, this should evaluate to 0, but then we OR with A, which is 1, so it's going to be 1. That's going to fail. So if we go back, we can just go undo that change we made to our XOR module and make it just XOR as we had originally. Okay, we've redefined that. And now if I rerun it, this test bench should work, right? Woo. Okay, it works. We can make an XOR. So in this case, for example, because we're doing combinational logic, there's no state, we can just kind of directly set things and don't have to worry about time. Starting next Monday, we're talking about, actually thinking about time in terms of cycles and registers and those sorts of things. and we'll come back to these kinds of details in a second. But that was it. We kind of did our goal, right? We went out and wrote our first little Chisel module. In order to get there, we had to understand a little about Scala, a little about Chisel, and a little about Chisel Test to kind of see how to interact with it. But there we go. We've seen the whole thing fit together. So I'm going to pause for any more questions. Cool. Okay. So before I let you all go, I just want to give you a couple quick administrative announcements. So I set the office hours for myself. So I'll be on Monday and Wednesday, including Wednesdays after lecture. So right after lecture, so 10:30 to 11:30. So go ahead and go onto the course Canvas to get access to the Zoom links. They're calling now while we're remote, but like everyone else, we're hoping to be in person in 2 weeks. And I'll be back in my office on campus. And then people asking about when's the first assignment going to come out. We're probably going to be posting the lab on Thursday or Friday, but it won't be due until next week. There'll be first lab, and then following the first lab, there'll be the first homework. And so that kind of a reminder to progression for this course is it'll typically be for a given week or unit's worth of material, there'll be a lab to kind of get first exposure to these concepts, a single line at a time, 2 lines at a time, kind of playing with it. And then in the homework, you'll do a larger project, right? And the labs are done via Jupyter, like this, very kind of short and easy. The homeworks you'll do inside of, your favorite text editor or IDE. I recommend IDE. Great. Any other administrative questions I can answer? Okay. Well, with that, I'll wish you all a good day. See you, folks.